Okay, let's begin. Welcome everyone to the Astronomical Society of Edinburgh. Tonight we have Dr. Roberta Zanin speaking to us from Bologna in Italy. So thank you very much for joining us, Roberta. I've just got a few introductory remarks just before we get started on the main talk of the evening. I can see we've got people joining us on YouTube from Vancouver, South Carolina, and Scotland. So welcome wherever you are in the world. We have our members on Zoom as well, and you'll be able to watch this on our YouTube channel afterwards if you miss any of it or you want to watch it again. As I said, I haven't done any slides for tonight because this is the first time I haven't done slides for a long time, but just too much happening this week. So I'm just going to share, hopefully you can see that okay, which is our website, and everything that we do you'll find on our website. So these are the talks that are coming up in the next few months. So tonight we obviously have this talk from Dr. Roberta Zanin about the Cherenkov Telescope Array Observatory. Sounds really good. Our next meeting will be on the 7th of April, and that is a members' night. So we will be broadcasting that particular one on YouTube, but it will be on Zoom for members and in person at the Augustine United Church. So if you are a visitor, you're welcome along to that in person at the church in Edinburgh. We're happy to see you there. On the 12th of April, we have our monthly imaging and observing group, and that is for members only. And then on the 21st of April, we have a talk from Dr. Michaela Musilova about simulated missions to the Moon and Mars. That will be on YouTube Live as well, so you can watch that there with us. On the 5th of May, we have an introduction to cosmology in the 21st century with the James Webb Telescope. That will be in person and also streamed live to YouTube as well. So it's a hybrid meeting. The 19th of May, very interesting, signing on with the Indigenous Australian Astronomy, Dr. Pete Kuzma. And then on the 7th of July, another hybrid meeting from Launch to First Science about the JWST's first year. And that will be in the Augustine United Church in Edinburgh on Zoom for members and on YouTube for visitors. While I'm on the website, I thought I'd just point out a few things which you might find interesting. Underneath our imaging and observing group menu here, we have quite a few meteor cameras in the society now, and if you want to see what they're recording every night, you can see that there. So each of these columns is a different camera that we have pointing in a different direction, and you can see we capture quite a few meteors, as well as airplanes and satellites and star trails, bats, moths, things like that as well. So quite interesting to keep an eye on what's going on there. We also have a Flickr group where you could find all the images that our members are posting. Some amazing images over the last few years, from deep sky objects to auroras to moon planets, galaxies, conjunctions, and just nice landscape shots as well. So that's worth having a look at as well. If you are a member or you want to join as a member, we do have a members area which is just for our ASE members who have joined, and every week you get a newsletter. So for example, this newsletter here had information about a previous meeting, about the videos, various presentations that we might have done, information about what's coming up in the next week or so. Alan Pickup gives us his monthly sky guide as well, and that's trailed there. Any observations that our members are making. So these are some nice pictures of auroras that we've had recently. Some news items. So for example, this new comet that may produce a nice show in 2024, and maybe a damp squib, information about that. Some information on a different topic that was this time about variable stars as well. So those are the sorts of things that you can get as a member, and we get newsletters like that every week as well. I'm going to stop that now, and I'm going to hand over to our speaker for the evening, Dr. Roberta Zanin. As I said, she's in Bologna in Italy, and really looking forward to this. So over to you. Thank you very much.
So thank you very much. It's a real pleasure to be here with you tonight. Yes, so I'm the project scientist of the Cherenkov Telescope Array Observatory, and I will try tonight to explain to. Oh, what happened? Do you see properly the video? Yes, no?
Yeah, we see the slides. Yeah.
Okay,
yeah, it's all
perfect.
working. Thanks. Yeah.
Okay. And yes, I will say, so this is the outline of the talk. So I will try to introduce the gamma ray astronomy. This is a fairly recent field in the astronomy world. And in particular, I will pause a second to explain how the imaging atmospheric Cherenkov technique works, which is the basis of the Cherenkov Telescope Array Observatory. So we will move to the explanation of this new observatory that is going to be built in the coming years. And then I will explain very shortly why it's interesting to look at the sky in gamma rays. And what is, I will conclude really with one slide of the project status, so to know when the CTAO will be online and ready to deliver data to the community. So we start with introduction to the gamma ray astronomy, and I start from far away in the sense that this is an image that we all know. It's a deep field image of the Hubble Space Telescope, and this is how, in general, we think about how we think the sky looks like. But we need to remember that the visible range of the electromagnetic spectrum is just a small fraction of it. And then if we compare the radiation from the universe to a piano, this would be a piano which is 15 meters long. So, and just to continue on this analogy with the music, which I think it's very impressive. So if we now, I let you listen to a song that you all know very well, but this song is played with just 1 octave, because we can compare the visible spectrum to 1 octave of these 15 meters long piano. And try to guess what's this song. And now I let you listen, but played with the full piano. And then it's, I think this is okay, so then this is just to give you the impression that we really need to be able to appreciate our universe and all the beauty of this universe. We do need to really play the 15 meters long piano. So we do need to look at the universe across the full electromagnetic spectrum, from the radio waves up to the highest energies, which are exactly the gamma rays. So now we go back to the astronomy, and then this is an image of one supernova remnant, which is very famous, and here you have a video again where you can see how the supernova remnant looks like if you look at it in different wavelengths. So this is a composite picture where we have put together all the images from the various wavelengths, and then you see here the 3 separate images in radio, X-rays, and optical. So each of these images really gives us different information, and only by studying all of them we can have, and we can really understand which are the mechanisms, the production mechanism at the basis of these objects. Okay, so this is another image. This is the Crab Nebula, where you can see it at different wavelengths, and you see how it looks like in radio, visible, and up to the gamma rays. So if you do this image, just to say, so the Crab Nebula is one of the brightest sources in gamma rays, and you see that these highest energies at these highest energies, the image is the poorest one because we have the worst angular resolution at the moment. But still, despite these, I mean, we will understand with this talk why it's really important to look at the sources also in gamma rays. So before going there, let's try to think about the gamma rays for a second and to understand how we can detect these energetic photons. So we are at the highest edge of the electromagnetic spectrum. And so these are the most extreme, we are talking about the most extreme radiation, which with a wavelength that is smaller than the size of an atomic nucleus, with an energy which is larger than 1,000 billion times that of the visible light. So gamma rays are the most extreme radiation, but are still a form of light. Although there is an important difference between gamma rays and all the other wavelengths. And the reason of this difference lies in this famous equation of Einstein. So Einstein has basically defined the relation between matter and energy, and all the photons up to the X-rays, for all the photons up to the X-rays, the energy is smaller than the energy that keeps an electron binded to its nucleus. This is not the case for the gamma rays. So what does it mean? I mean, in first approximation, it means that we can produce radiation up to the X-rays with the there's something, okay, well, sorry. Up to the X-rays, we can produce it by heating matters. So this is what we call the thermal radiation. Of course, I'm not saying that all radiation up to X-rays is thermal, but I'm saying that it can be thermal. There is no way that we can have thermal radiation in gamma rays. I mean, and this is really easily understandable if you think that the energy of a gamma ray is larger than the energy that keeps an atom together. So the matter would disintegrate before reaching the temperature at the gamma rays that would need to require to produce gamma rays. So this means that if we really want to look at gamma rays, we need cosmic accelerators. We need some accelerators that are able to accelerate cosmic charged particles. And these charged particles that we call cosmic rays, when they interact with the matter, then they produce gamma rays. So the way we have to observe these gamma rays is very different with respect to the other type of astronomical fields. So before, let's say, below the X-rays, we can use lens and mirrors. There can be different types of lens and mirrors, but still, this is the way we have to really look at these photons. Whereas for the highest energies, we cannot use lens and mirrors, but we do need to use detectors that are more similar to high energy particle physics. And then we use basically if we want to look at the gamma rays from ground, what we do is to observe the secondary particles that these gamma rays produce when interacting with the Earth's atmosphere. So we now move to try to understand how all these works. This is really the basis of the imaging atmospheric Cherenkov technique. Here you have a video of one of the currently existing facility of this kind. So if you look at the telescope, it looks more like, let's say, an antenna, so a radio telescope, but there are mirrors. So how does this work? So the idea is, as I was explaining before shortly, is that we have we have a gamma rays that when enters the atmosphere, it produces a cascade of particles and this cascade of particles are moving towards the ground. And this is what you can detect with a certain type of telescopes. But this is not what the imaging atmospheric Cherenkov telescope do. So these telescopes do not detect the charged particle, but instead, if we really look at the video, so you see that at a certain point, there is some blue light that appears, so a front of blue light that appears and travels down to the ground. So this is the Cherenkov light, that these charged particles that are moving at a velocity, at a speed which is larger than the velocity of the light in the medium, they produce, and this is what we detect. So there are telescopes with huge reflective surface that can collect this light and focalize it into a pixelized cameras. And in this camera is where we can reproduce the image of the cascade. So the cascades, as I said, I mean, I talk about gamma rays, but we know that in our atmosphere, so there are millions of cosmic rays arriving every second, and these cosmic rays, they do interact as well with the nuclear, the atmospheric nuclei, and they produce as well a cascade of secondary particles. This is what we call extensive air showers. And so what the tricky point of this technique is that we do need to distinguish between the cascades of secondary particles that are produced by primary gamma rays with cascades produced by cosmic rays, by charged particles. And I mean, I don't want to go into much details, but you see here that the type of particles that these that are produced in these cascades is different, and also their development is different. So if we manage, now we will see in a second how we will manage to distinguish between these two type of showers. I want just to draw your attention on one specific factor that is what you see here. So you see that there are within what we call the cosmic ray induced showers, there are showers that are purely electromagnetic. So they are equivalent to what is a shower induced by a primary gamma rays. So these for us are a source of irreducible background. We will not ever be able to distinguish this kind of sub-cascade from the cascade of the primary gamma rays. So this is another additional point that made the technique difficult at the beginning, so that it required quite some software development to reach the point where the background rejection power was high enough to be really successful in the detection of the sources. So this is just a simulation of the two type of cascades, just to make you, I mean, this probably is better visualized how they look different, especially in the longitudinal, but mostly in the lateral development of the shower. So as I said, we do not detect directly the particles, but we do detect these, but we do detect this Cherenkov light. The Cherenkov light that is traveling towards the ground as a front, and it's a flash which is super fast. So we are talking about 10 nanoseconds duration of flash. So the Cherenkov light is visible light. So these are a special kind of optical telescope that do detect the visible light, which is produced by this cascade of secondary particles. So basically, we have a reflective surface that collect this visible light into a pixelized camera, which is a camera of photomultipliers. And here another tricky point of this technique is that we do need fast readout system to be able to really distinguish and detect these 10 nanosecond flashes within all the night sky background that we have. So how can we really distinguish the gamma ray induced showers, so which are what we call our event? So the type of showers that are produced by the gamma rays that we want to study, and discriminate them from all the other events that are instead produced by cosmic rays, by charged particles. So here you have the image of one gamma rays, as we do see in one of the camera of the existing facilities. And you see that this has an image, we call it image, and it can be parameterized with an ellipse. And this ellipse, I mean, if you look at the major axis of the ellipse, this gives you basically the idea of the direction of the primary gamma rays. And if we integrate the amount of charge that there is in each pixel, this is proportional to the energy of the primary gamma rays. So then it's much more complex than this, but in first approximation, it's easy to understand that we can retrieve the information, the basic information about the primary gamma rays by studying the images of these of the shower produced by the primary gamma rays. If we instead look at an image in the camera produced by a proton, by a charged particle, then you see that the image is is very different. So first of all, it's broader, and it's also pointing in a random direction. So it's not pointing towards the camera center that gives you the pointing direction of the telescope. So basically, we can distinguish between the two type of events by looking at the eccentricity of the ellipse, also from the direction of the primary particle. So it's a kind of, so at the beginning it was done by using really basic parameters. Now we use random forest neural networks that are much more efficient and really increased the capability in discriminating the background from the signal, and this of course improved the sensitivity of the technique. So this technique has been established at the end of the 80s. So the first source was detected was the Crab Nebula, as I said, in 1989. And it was detected by the Whipple Observatory, which is located in Arizona, in US. And since then, this was a standalone telescope of this kind, so an imaging atmospheric Cherenkov telescope. And after that, there was a second generation of telescope of this kind was built, and this second generation detected few sources, really a handful of sources. After these, it was still proven to be an improving technique, and now we have the third generation of this kind of telescope. These are all arrays of telescopes now, so with few units of telescope, and there are 3 facilities of this kind all around the world. So one is Hess in Namibia. One is Veritas, basically close to the same site of Whipple, so in Arizona, Tucson, US. And then there are the 2 Magic telescopes in the Canary Island of La Palma. So these are, as I said, are still working, are still operating, still providing exciting results. And as I was saying, so in 1995 there were 3 sources detected in the energy band, in the very high energy band. Nowadays, so after these, the advent of this third generation of arrays of imaging atmospheric Cherenkov telescopes, we have more than 200 sources. So nowadays we have almost 250 sources. You see here that, so these are, half of them are distributed along the galactic plane and half of them are of extragalactic origins. Among these sources, we can identify more or less a tens of different classes of sources emitting at this energy. So basically, this tells you that the technique now has been proven successful, and we have moved in the last years from really the detecting machine to really doing some astrophysics. We are still not at the place where we can do population studies. So we are really at the entering the astronomical world now with the first precision measurements, but we do need to move further, and we do need to go one step further to really join the astronomical community and being able to detect much more sources, produce population study, as well as going deeper in the analysis of the data, and then produce much more precise results. So that's the reason why, more or less 10 years ago, scientists started to think what was the next step. And here, just to give you the impression, this is our Milky Way, and you see here the horizon of one of the existing facilities has. So you see in red that has explored just a small fraction of our Milky Way. And this is if we consider only point-like sources. Then if you instead consider extended sources, then the volume that has been explored is much smaller, is what you see here in blue, because the sensitivity decreases with the extension of the sources. So now the idea was to build something that was able to really explore the entire volume of our galaxy for what concerned the galactic science, but then we would also want to have an instrument that could go much further away in the volume of the universe that can be explored. So the design drivers that were put forward are sensitivity. So we wanted something that had a sensitivity a factor 10 larger, so better angular resolution. So we're talking about arc-minute angular resolution, 10% energy resolution, but also we wanted to have something which, so an instrument which could have a larger field of view. So the currently running facility have a field of view of about 3 to 5 degrees. Now, at least would have needed at least a factor 2 field of view to be able to study the more extended sources and large structures. And another important point is the wide energy range. So these facilities that are currently running are looking at the sky more or less between 100 of GeV and a few tenths of TeV, so giga electron volt. And so we are talking about giga electron volt is 1 billion times larger than the optical photons, and tens of tera-electron volts. So we want to have something with a wide energy range, so moving up in energy in a region which is still very poorly explored, so above tens of TeV, and then down to 20 GeV. So then let me just pause why it is relevant to go down to 20 GeV. So the gamma rays that are traveling from the far universe towards the Earth are absorbed by the extragalactic background light, as we will see in a second after, in some slides after, at the end of the talk. And this absorption is energy dependent. So the only way we have to really look at the dawn of the universe is to go to an energy where this absorption disappears. And this is about 20 GeV. So by looking at 20 GeV, you can really start exploring the universe at its dawn. So you see here just a sketch to visualize how the volume of the explorable universe improves from the currently running facility and what we expect from the next generation of facility of this kind. So that's why the idea of this was the idea below the Cherenkov Telescope Array that was conceived, as I said, 10, 15 years ago. And the design, so how can we, naively speaking, how can we obtain a factor 10 improvement in sensitivity? So we saw before pictures of the currently running facilities, has Magic and Veritas. They all have a few units of telescopes. So here I put 4 telescopes. And if you have 4 telescopes and then you have an event coming in, you see this one is perfectly seen by the four telescopes. But then if you have another event that arrives here, this is seen only by the one of the 4 telescopes. So the reconstruction that you can have in terms of direction and also energy is very poor. Then you can miss a lot of events, of showers. And the way you can have to improve these, the sensitivity of the instrument is to multiply the number, so to increase the number of telescopes. And naively speaking, you can think that the sensitivity improves as the square root of the number of telescopes. So the basic idea is, okay, you want a factor 10, let's go for 100 of telescope. If you have a large array covering a much larger footprint, basically you can reconstruct perfectly in a perfect way a much larger number of events. And this is actually the idea of the telescope, the Cherenkov Telescope Array. So to have, let's say, hundreds of telescope of this kind, we know that the technology is very mature now, and it's proven mature, so we can really use it and exploit also in let's say in an astronomical way, as we will see in a second. So the another important point is that we didn't only multiply, so we didn't take the design of the existing telescope and then just looked for funding for funds and try to build 100 of them. But the design was really optimized to trade off costs and scientific necessity. And this exercise ended with the definition of 3 different designs. So we have the small-sized telescopes, medium-sized telescope, and large-sized telescope. Each of them is optimized for one specific energy range. So we have the LST, the large one, which are optimized for the lowest energies. So let's say below 100 giga-electron-volt. And the idea here is that if you want to look for low energy events that for us are anyway tens of giga-electron-volt, you do need to have a large reflective surface, because these events produce just a little of Cherenkov light, and you need the large surface to collect most of it. On the other hand, if you want to optimize for a telescope, optimize for the highest energy, so we are going hundreds of TeV, These events, so an event produced by 100 TeV gamma ray would produce a lot of Cherenkov light. So you don't need large reflective surface, but instead you do need to have a large footprint. So many telescopes to be able to detect just a few photons that arrive at this energy. So this to say that the design of the array foresees to have few large size telescope at the center, and then a ring of medium-sized telescope and an outer ring of small-sized telescope. So covering basically 3 square kilometers area. So the another important point of this new facility it should have the largest possible sky coverage, and this is guaranteed by the fact that we have two observation stations, one in the northern and one in the southern hemisphere. So the northern one is located at the same site where the MAGIC telescope are, so at the Canary Island of La Palma, and which is at the Observatorio Roque de los Muchachos, and the southern one is in Isoland, so at Isoland in Paraná, in Chile. So this observatory has been fully funded in its initial configuration, and this initial configuration that we call Alpha foresees 4 LSTs and 9 MSTs in the north, and 14 MSTs and 32 SSTs in the south. So you see here that the southern one has a much larger footprint, both for scientific and orographic reasons. I mean, the site at the north is much more complex, so it's up to a mountain, and there is a little less space, but it's also because it is focalized, it is focused on the extragalactic science that is related to the lowest energy, so that it requires the large size telescope more than a large footprint. On the other hand, the southern array is more focused on galactic science, and the galactic science is that we know that the highest energies can be produced only by sources that are close by within our galaxies, and that's the reason why the southern sky, where our Milky Way is better visible, is also the largest one with a large amount of telescopes. So before I talk about hundreds of telescopes, this was the full scope configuration that we had to compromise with the available funds, and that's why we came up with this initial configuration that we do hope to keep. So we will keep looking for funds and to build further more telescopes in the coming years. So this is the sensitivity with us. So this is the minimum, the sensitivity as a function of the energy for the northern and southern array, so black and red. And what the message I want to convey here is how this compares with the currently running facility, which are represented here by these purple lines. So you see that we do reach factor 5 to 10 improvement depending on the energy, and we certainly enlarge the range, the energy range with respect to the existing facility of the same kind. The sensitivity, so the minimum flux that can be detected in a certain amount of time, is not the only important parameters, but another important parameter to really be able to study in detail the mechanism that produce this radiation is also the angular resolution. And here, just to give you an idea, so this is Centaurus A. So with the field of view that is expected by CTAO, so you see here how it looks like at radio wavelengths, and how far we are with our angular resolution from these kind of images. But still, I mean, this gives you the idea of what can be done in gamma rays with the existing facility and with the future one. So this is the image of Centaurus A's with the seen by Hess at 3 TeV, more or less. And this is the point-span function of S. So this is what we expect with CTAA, so the kind of improvement. And just to compare with other gamma ray detectors at different energies and using different techniques. So I mentioned before that CTAA is an observatory. So this is really a step forward, a huge. It's really a change with respect to the what we have now in the field of the gamma ray astronomy, where all the facilities are experiments with proprietary data, proprietary software. Instead, CTAA will be the first proposal-driven observatory where scientists around the world will be able to apply for observing time, and this proposal will be evaluated as it in all astronomical observatory by a time allocation committee. The data will have a proprietary period of about 1 year. But after this period, the data will be publicly available to all without any restriction, and this will be delivered together with the science analysis tool to foster, to really help the users that are not coming from other astronomical community to start looking at the gamma ray data. So this observatory will also be able to follow up on science alerts produced by other observatory. This is especially special importance in this moment with the multi-wavelength and multi-messenger astronomy. And it's one of the key science program to follow up on gravitational wave event, as well as ultra high energy neutrinos and any kind of transients, which is very often related to the extreme explosions that can produce the highest energy radiation, like gamma rays. So why to look at the sky in gamma rays? So the gamma rays, as I said, are produced by the interaction of the charged particles with other material. And these, so there are, we know nowadays that there are like tens of different sources, class of sources that can emit these energies, and it's where you can have particle acceleration, and these particles are accelerated up to relativistic energies. So this happens either in the shock of a supernova remnant, and after the blast of the supernova, there is the shock produced with interaction of the interstellar medium. It can be produced in jets of active galactic nuclei. It can be, you can have a particle acceleration up to these energies also in events like the gravitational, the merging of neutron star, or neutron star black hole that has not been seen so far, but these produce what we call the gamma ray burst, a short gamma ray burst that comes with jets, and in these jets we have particle acceleration up to the relativistic energies, and these are the gamma rays that we can look at. And why to look at them? Because they give us a different picture. So we can really try to understand where these particles are accelerated up to these highest energies by looking at the gamma rays. So this to gives you an idea. I mean, at the end, so this will allow us to study these kind of sources. But so this is the galactic plane survey as we know at the moment, with more or less 100 sources detected so far at these energies. So you see that there are a few spots, whereas this is the simulation that we have done and what we expect to see with CTAO. So the number of sources really increases by a factor 5 to 10, depending on the classes of sources, and these really will give us the possibility to start studying, start producing population study of the different class of sources, and also to study in detail the how the gamma rays are produced in these different classes, which are the analogies between the classes, and and this kind of studies. So it's a matter of not only a matter of number of sources, but really on the precision of the results that you can reach with this new instrument. CTAO, as well as the currently running facility CTAO, will go one step further. But so these instruments are also important to really study the origin of the cosmic rays. So this is the usual cosmic ray spectrum that covers several decades in energy. So the cosmic rays have been discovered more than 100 years ago, but still their origin is a little bit mysterious. The origin, so we know that there is this feature, so the highest energies are of extragalactic origin up to what we call the knee. So this part here should be produced within our galaxy. But which are the sources that can indeed accelerate particles and produce these cosmic rays? So we saw different kind of sources before that, and I mentioned the supernova remnant that can indeed produce accelerate charge particles up to relativistic energy. So this has been proven too. But the still open question is, can they accelerate particles up to the PeV energy, so the per electron volt energy, so up to the highest energies that we believe are of galactic origin. So and this translates basically in the search for what we call the pevatrons, so the sources that can accelerate particles up to the highest energies. And we do look at sources in gamma rays, because we know that when there is so the mechanism is that when you have a charged particles interacting with some interstellar material, then this produces gamma rays. And the relation we need to remember is that for a PeV proton, what you will get is 100 TeV gamma rays. So here the trick, if you want to look for pevatron sources, is to look for gamma ray sources at hundreds of TeV. So right now, in the last years, there were important discoveries in these fields. There are different kind of instruments that really detected the first sources above 50 TeV. Here you have the galactic scan by the Hawk collaboration. And in the last years, also LASO became online. This is an instrument in Tibet. Then this released and published spectra up to hundreds of TeV for 12 sources. So the point is that I want to make is that, so now we know that there are pevatron sources. So these results that we have from these different kind of instruments are showing that there are photons at these energies. But given their angular and energy resolution is basically impossible to say at the moment if this emission is indeed produced by the charged particles, by the cosmic rays. So these are the cosmic rays that we are looking for, instead of being only leptons accelerating with a different mechanism and produced with a different mechanism. So this is still one of the open and hot questions in the astronomy, that is in the gamma ray astronomy, that is very much related to the cosmic ray physics. So the usage of gamma rays to really study the cosmic rays. At the moment, so the few years ago, everybody would have said, okay, these cosmic ray accelerators are the supernova remnant. Nowadays, we know that there are some problems with the supernova remnant. So either they are pivotal just for a small fraction of their life at the beginning of their life, but certainly when they become older and older, they cannot produce accelerate particles up to this energy anymore. So they can be, we can have our black hole at the center of our Milky Way could be a pivotrons. There are other hypotheses that the star-forming regions can indeed be the site where these cosmic rays are produced. But this is really a new field, and it's where most of the gamma ray astronomers are investing their time. Another interesting aspect of the gamma ray astronomy is that you can do cosmology. As I said before, so the gamma rays, while traveling towards the Earth, are absorbed by the extragalactic background light, which is the light by star and dust produced during the universe life. And so this means that if the spectrum of a source is intrinsically like this, when you measure it at Earth, then you see something like this. So you really see a feature in the spectrum that can be used to really study the extragalactic background light. So the what we call the EBL. The EBL is something that you can measure directly. There are many measurements, but and we know that the extragalactic background, the EBL has two main peaks, one in optical, one in infrared, and this peak here is really poorly constrained because there is a lot of foreground, and it's difficult to get direct measurements. So by using gamma rays, we could provide, and looking at the spectra, the feature in the spectrum that these EBL absorption produce on the spectra of distant AGNs, distant blazars, we can really study the EBL and measure the EBL also in at these wavelengths. So this is another usage that you can do of gamma rays. I stop here with science. I have just the last word about the status of the project. So I said that this has been funded. So we are about to start the construction phase. Although there is already a prototype that is currently under commission. It has been inaugurated in a few years ago in the Canary Island of La Palma. This is the first LST, and it's already producing the first scientific results. This is still a prototype, has not been accepted by the observatory yet, and the main reason is that as I said, so the construction scope has been agreed just 1.5 years ago, and the construction phase can start only with the establishment of the final legal entity, which is the ERIC, so the European Research Infrastructure Consortium. that is really at this time is about to be established. So we are just waiting for the last step, and now we hope to have it to have the European Commission final blessing either in July or in June, July, or maximum September. So with the establishment of the ERIC, the construction phase will start. And then it is supposed to last about 5 years. During these 5 years, we will be building an increasing number of telescopes with time, and as soon as they are operating, then the early science can start. So we will have the first scientific results, let's say, in a couple of years from now. So this observatory is geographically distributed. We talk about the 2 observation stations, but the headquarters are sitting in Bologna, so in Italy. And we also have a science data management center in Zeuthen, close to Berlin, in Germany. And then I stop here. So really, basically, my last sentence is to say that CTAO will be a phase transition in the very high energy astronomy. So, and it will open to the entire astronomical community its data, so that we can really, any scientist in the world can use this data to study his or her preferred source. And at the same time, I mean, this is really expected to provide an in-depth understanding of known objects, but also unexpected discoveries of new classes of objects that so far have not been detected by the existing facilities. And then, as all the instruments with such a giant leap in performance, we also hope to see things that we haven't thought about. So, and this will certainly be the most fun part. And that's it.
Well, that's amazing. Thank you very much. Can we thank Dr. Zanin before we move on to questions, please? That is quite a different way of looking at the universe than maybe most of us are used to here as well. So it's quite amazing. As usual, if you've got questions, put them in the chat on Zoom and chat on YouTube, and we'll get around to them as well. Question I had, in terms of the cost of these telescopes compared to maybe an equivalent optical telescope, say, how does that compare, the cost-wise?
I mean, they are much cheaper. So we are talking about, so this whole project is about 300 millions euro.
Yeah. So quite a lot cheaper then, yes.
Yes.
Yeah, it's quite a lot cheaper, right? Yeah. Okay, have we got questions, Peter?
And the reason why these are cheaper is because I mean, we do not look directly at the optical photons, but we do reconstruct the showers. So we don't need such a precision that you do have for optical telescopes. So that's the main reason why these are much cheaper.
Yeah. Does having telescopes spread across the world help with the resolution, or is that not of interest really?
Not really. I mean, no. You reach a point where so the resolution is not related. So it improves with the number of telescopes up to a certain point.
Right. Okay.
And then it's related to to other aspects of the telescope, but not the number.
Right. Okay. Thank you.
So why you don't go into space? So the reason is that in space, so you know that there is Fermi-Lat, for instance. So Fermi at the collection area that a satellite can have is about 1 meter or something, like 1 square meter, something like this. But if you really want to go to the highest energies, you will not be able to detect the highest photons, let's say tens of TeV in a satellite, not even integrated over 30 years or 10 years. So you do need to look at them from ground to be able to have such a large collection area.
There was an interesting comment from Stuart, which said something like, for most astronomers, the atmosphere is a nuisance, but here it's actually useful, even essential, which is quite interesting.
It's part of the detector. We usually say that it's our calorimeter.
Yeah, that's right. Yeah.
And then Ramsey, you got a question?
Can you observe? Sorry.
I was just wondering if you could observe 24 hours a day, or is the sun a source of noise?
Sun is a source of noise because we look at the optical light at the end. So it works as an optical telescope in this respect.
Okay, thanks.
That's everything on Zoom at the moment, Mark.
Yep. The only comment we had on YouTube was that David said he's visited Magic 1 and 2 on La Palma. So here we go. Okay. Are there any more questions? If not, then I think it's all. So can we thank Dr. Zanin again for that talk? Really interesting. Thank you very much. Really enjoyed that. Thank you.
You're welcome. Thank you to you.
I see you've got the Royal Astronomical Society on your slides. We're not actually royal. We are the Astronomical Society of Edinburgh, but the King hasn't given his assent to us. So
okay, sorry.
That's great. Okay, thank you everyone for joining us. Thank you especially to our speaker tonight, and we'll see you at our next talk. So thank you very much, everyone. Good night.
Thank you. Bye-bye.
Good night.
Bye.
Night.